Hello and welcome to T2 Day 18 of Honors Precalculus. We're going to talk about vectors today. So first, some quantities can be represented by a single real number, and those are called scalars. So they are called a scalar that indicates a magnitude or size, one or the other. So things like speed or area, distance, volume, height, temperature, things that are noted by one real number. Some quantities have both magnitude and direction. So for example, velocity, force, or acceleration. So for example, speed is a scalar, it's only one number, it can only be positive, but velocity could be forward or backward or in any of these directions. It can be in any direction. So quantities that have both a magnitude and direction are things like velocity or acceleration or force. So you can have force in different directions and different sizes, velocity in different directions and different sizes, and acceleration in different directions and different sizes. We're going to represent these second things with vectors. Vectors will give us a size, so the length of the vector, and a direction, the direction of the vector, right there. So this vector is called PQ because it goes from point P to point Q. We'll put it right there. P is the initial point and Q is the terminal point. So you put the initial point first and the terminal point name second. So it's called P to Q. And you must have that little hat up here. See that little hat? It's very small. So it needs to be PQ with an arrow. That means vector PQ. Now, if you want to know what just the magnitude is, which is just a scalar, a single number, you note that with these two bars right here. So this would just be the length, the magnitude of the vector. So let's do a vector problem. So given the vector u is from r equals negative 4, 2, so negative 4, 2 is right there. There's r. To s, which is at negative 1, 6, which is right here. So it goes from r to 6, a little arrow in that direction. You can make the heads a little bigger if you want to. And vector v is from 0, 0 to 3, 4. So 0, 0, so point O, and p, which is 3, 4, right here. There's these two vectors right there. Prove that u is equal to v, i.e. they have the same magnitude and direction. So the direction is the slope. You can think of it as the slope. So from u to v, so from r to s, let's do that first. From r to s, you're going to go over 3 and you're going to go up 4. So what you can say, the direction of u, vector u, and we'll do vector u like that. The direction of vector u is going to be the change in y over the change in x from r to s. And that's going to be 4 over 3. That's the slope. And then what's about the direction of v? That's the same thing, same measurements. In this case, it goes over 3 and up 4. So in this case, it is the same. They do have the same slope. They have the same direction. So we've verified that they have the same direction. What about the magnitude? How do you do the magnitude of vector u? Well, that is going to be the same distance formula that you've seen before, which is going to be x2 minus x1 squared plus y2 minus y1 squared, all underneath the square root sign. And in this case, that's going to be the square root of 3 squared plus 4 squared, which is 5. Square root of 25 is 5. Similarly, when you do it for v, you end up with the change in the x direction and the change in the y direction squared. That's those two values. And when you do this out, you also end up with 5. So what do you have? The same magnitude and the same direction. So we now know that vector u is equal to vector v. They are the same vector, they're just in different places. Mathematicians like to write the same thing in different ways because they can be helpful in different forms. The component form of a vector is this form right here, this form right here. It's equal to the vector with the initial point 0, 0 and terminal point v1, v2. And you write it with these brackets. These are a little wider than I write, but they are brackets. Usually you see them as like the less than and the greater than symbol right there. So what does that mean? Let's just go back for a second and see this here. This vector right here, vector u right there, one way to write that would be 3, 4, meaning wherever you start, let's say at 0, you would go over 3 and up 4. And it's the same for vector v, over 3, up 4. But the component form doesn't give you the starting point. It could be anywhere. So if you wanted the magnitude, all you do is you square the components. So let's clarify that by doing an example. If I draw the vector 3, 2 in 3 different positions, you can put them in 3 different places. So I'll put it at the origin. That means you go over 3 and up 2. So this vector could be here. Or I could start here and go over 3 and up 2 to there. Or I could start here and go over 3, and up 2. This vector v is these are 3 representations of v. You can start anywhere you want. Now to do the magnitude of v, all you do is you square root 3 squared plus 2 squared, which is going to be the square root of 9 plus 4, which is the square root of 13. That's all you do to find the vector of v. So when it's written in component form, finding the magnitude is great. What about this vector right here? And you will notice that I like putting hats on every time we have a vector, even if the word vector is before it. -2, -4. So I could start at the origin, and that means go back 2 and down 4 to here. So it could be here. I could start here, back 2 and down 4. It goes here. Or I'm just arbitrarily picking a start here. You can start anywhere you want because component form doesn't give you a starting point. So vector u here is represented in 3 different ways here. What's the magnitude of u? And I'll use regular marker there. It's going to be the square root of -2 squared plus -4 squared. See the parentheses? Make sure you do that. So it's going to be 4 plus 16 is root 20. And yeah, you could do that as root 4 times root 5, which is 2 root 5. Either one is fine. I would accept either this or this. That's fine. You don't have to simplify the radicals unless you have to. So in this one, it says find the component form of the vector where it gives you the starting point and the end point. And you know it's the starting and end because it goes P, then Q. So what you can do is just draw a picture. You go back 3 and up 4 to get to the first point, P. So P is right there, and Q is at -5, 2. So -5, 2 is right there. So that's the vector PQ, and P was -3, 4, and Q was -5, 2. So to get the component form, you would do where you're ending up x value, -5, and you would subtract -3, comma, 2 minus 4. So you're doing really, remember, it's going to be, it's the ending x value. So the ending x value was there. So that's where that -5 is. And then you have the -3 here, and you're subtracting in both cases. Remember, you subtract. It's the distance between. So you end up with this vector v being -2 comma -2. And to do the magnitude of that, and I'll make these v's look as much like v's as I possibly can, v, you end up with the square root of -2 squared plus -2 squared. It's going to be the square root of 4 plus 4 is the square root of 8. And you can leave it like that. That's totally fine. Or you can keep going and make it the square root of 4 times the square root of 2, which is 2 root 2. Either one is fine. Either one is fine. So just like many times in the past, draw a picture, see what happens. In terms of vector operations like addition, you do exactly what you might think you do. If you have two vectors, u1, u2, and v1, v2, if you add them, you literally just add the first two terms and the second two terms. So you would take these two terms, add them together to go there, and then you would take these two terms and add them together to go there. That's it. Now, if you have a scalar, meaning a number on the outside, k here, k on the outside of a vector, it literally distributes on the inside to both terms. You can multiply in, which means you can go out as well. So let's do another example. If you have u and v, find the component form of the vectors below. What is u plus v? Well, if we do this out, we can do it out algebraically and we can draw it. So what that means is u is -1 comma 3, and we're adding 4 comma 7. So what you do there is you add these two together. So it's going to be 3 comma 10, because 3 plus 7 is 10. One way you can see that, though, is you can graph u and graph v from the end of it. So if we graphed vector u here, that's back 1 up 3. We'll start at the origin. So it's back 1 and up 3. It goes to here. This right here is vector u. So then if I then take v, so that was u there, take vector v, it would be 4, 7. So over 4, 1, 2, 3, 4, up 7. 1, 2, 3, 4, 5, 6, 7. This right here is vector v. I've taken v and I've put it on the end of u. Now where is u plus v? U plus v is this new vector from here to here. That's this vector here is u plus v. And you'll notice that if you go over 3, so over 3, and you go up 10, that's what that vector is. This vector is 3 comma 10. So you can do it visually, and you can do it just with multiplying it out. So let's just multiply this one out. So 2 times u, so that's 2 times -1, 3, plus -1 times v, 4, 7. First, multiply it in. So you end up with negative 2, 6, plus negative 4, negative 7, and now you just add. So that's going to be negative 2 minus 4, comma 6 minus 7. I'm just adding the components. So when you do that out, just make sure you go nice and slow, because it's really easy to make small algebraic mistakes. Really, really easy to make small algebraic mistakes. You end up with negative 6, comma negative 1. That would be the answer here. One of the best, kind of easiest, kind of awesomest vectors to work with is a vector that's a unit vector. And unit vectors have a length of 1. Any vector with a length of 1 is a unit vector. And so if v is not a unit vector, how do you turn it into a unit vector? Well, you divide by its magnitude. Think about it this way. If a vector has a magnitude of 5 and you shrink it by a factor of 5, by dividing by 5, you get 1. So you're dividing by the magnitude of the vector. So if you want to turn something into a unit vector, let's say you had a vector v that doesn't have a magnitude of 1, you divide it by its magnitude. So that's what's going on right here, and you will get a unit vector in the same direction. Multiplying by a scalar, dividing by a scalar, does not change the direction of a vector. So what does this mean here? Find a unit vector in the direction negative 3, 2, and verify that it has a length of 1. So if we go in that direction, we can just draw this here. If we started here, down, I'll put it down here to have space. Back 3, up 2. So this vector right here is vector v. That vector v is negative 3, 2, because it's gone back 3 and up 2. What is the magnitude of v? Well, that's going to be the square root of negative 3 squared plus 2 squared, which is the square root of 9 plus 4, which is the square root of 13. So this is not a unit vector because it has a magnitude of 13. So how do we turn this into a magnitude of 1? Well, you take the vector v and you divide it by the magnitude of v. And you'll notice sometimes I use double bars. That also means magnitude. You can do that as well. So that's going to be the vector negative 3, 2, the vector negative 3 divided by root 13. And you can write that literally as negative 3 over root 13, comma 2 over root 13. You can leave it just like this. How do we verify that that has a magnitude of 1? Well, you do the same thing. You do the square root of negative 3 over root 13 squared plus 2 over root 13 squared. If you square those, we're doing the magnitude. That's the magnitude of that vector. You would end up with 9 over 13 plus 4 over 13, which is the square root of 13 over 13, which is 1. So this right here is the unit vector in the same direction. In the same direction. There are two special unit vectors, the I and j vector. The I vector is just 1, 0, and the j vector is 0, 1. So this is horizontal one unit and vertical one unit, and they are called the standard unit vectors. The standard unit vectors right here, very important term. All other vectors can be written as expression in terms of these vectors. So what I mean is, if we had I is equal to 1, 0, and j is equal to 0, 1, how would we write 5, negative 3? Well, that literally is just 5 times 1, 0 plus negative 3 times 0, 1. Literally just that, because this is I and this is j. You can write this as 5i, I like the hats, minus 3, this is j right there. That's j, 3j. So you can write them as linear combinations is what they're called right there. Those are two important vectors, and this would be your final answer.